Hello everyone, today let's take a look at Quantipus number 56, another combinatorics one. So basically we have 5 children standing in a line at an ice cream truck that offers exactly 3 flavors, vanilla, chocolate, and strawberry, and you cannot mix the flavors, so each child will receive exactly 1 cone. So now we're actually pivoting a little bit from what we did in Quantipus number 81. In 81, we were splitting up distinct objects into identical groups, but in this one you notice we're splitting distinct objects into distinct groups. That's because you can think about it like the children are the distinct objects that are getting split into the groups of either getting a vanilla cone, a chocolate cone, or a strawberry cone. So because we're doing distinct into distinct now instead of distinct into identical, we can kind of forget about all of the integer partition stuff. So we're actually going to be able to solve this without enumerating every single partition and using more classic counting techniques. And looking at this problem first will just help when we're doing distinct into identical later and looking at Stirling numbers of the second kind. So let's look at part A first, which is going to be really easy. And how many ways can you hand out the cones? So you can see I drew 5 little children here and an ice cream truck. And this ice cream truck obviously has 3 flavors. It's going to be vanilla, chocolate, and strawberry. So every child needs exactly 1 cone. So child 1 could get anything vanilla, chocolate, or strawberry. So they have 3 options. Child 2 has the same choice, vanilla, chocolate, or strawberry. They also have 3 options. Everyone's going to have 3 options. So the answer to part A we know is just going to be 3 to the 5th. So now let's just move on to part B, and how many ways can you hand out the cones so that all 3 flavors are used at least once? So this is just the basic inclusion-exclusion setup. We know that there are 3 to the 5th ways of giving out the ice cream cones unrestricted, right? So all we have to do is subtract off the cases where any flavor is not used. Okay, so first let's say what are the number of combos without vanilla? Well, we're just going to have 2 different flavors left to distribute to all these kids. They all need at least 1, so now they all have 2 choices, right? So everyone has 2 flavors to choose from in this situation, so it's going to be 2 to the 5th. Okay, so now let's uncross off the vanilla, and let's say what are the number of combos without chocolate? Well, now every kid is just going to have 2 flavors to choose from, right? Vanilla or strawberry, so the same answer, we're going to get 2 to the 5th. And then you can see that if we cross off strawberry, so our only options are vanilla or chocolate, well then we're also going to get 2 to the 5th. By the way, we're just solving for this right now. But wait, we know that by inclusion-exclusion, we're doing a little bit of overcounting here. For instance, when I crossed off vanilla and I counted the cases with no vanilla, there would have also been some cases in there with no chocolate, right? When every single person would have gotten strawberry. So I'm overcounting the cases where vanilla and chocolate were both 0. And likewise, I'm overcounting the intersection of every single pair of 2 flavors, right? We have 3 flavors, so there's going to be 3 choose 2, different ways to choose 2 flavors. And when I cross off 2 of these flavors, well, there's only going to be 1 combination where every single person gets 1 flavor, right? These are all going to be 1s. So this is just going to be times 1 to the 5th, which we know is 1. And we don't need to do anything more because obviously I can't have a triple intersection of all zeros because everyone needs to get at least 1 flavor, right? So again, super basic inclusion-exclusion, we had 3 to the 5th total cases. So subtract off our single intersections, right? 3 choose 1 times 2 to the 5th, and then we're going to add back on our double intersection. So 3 choose 2 times 1 to the 5th. So 3 to the 5th is 243 minus 3 times 32, which is going to be 96 plus 3. Final answer, 150. By the way, the first one was obviously 243. So now let's go down and look at part C finally. So I'm just generalizing what happened in part B to when we have n kids and k flavors. So first for our total, we have n kids and k flavors. So each kid has a choice between k flavors. So we basically take k to the n. Then we subtract off the k choose 1 ways to choose a flavor that we're not going to sell. And then we're just going to have k minus 1 flavors remaining to distribute to the n kids. Pattern's pretty clear at this point. We're just going to continue doing inclusion-exclusion. We've done this a million times. K choose 2 is going to be our next one. K minus 2 to the power of n, etc. Let's make a summation formula. So I have a sum here with some iterator. Let's call it j. It's an alternating series starting with a positive term. So let's throw in -1 and raise it to the power of our iterator and start our iterator at 0. Add in the binomial term where obviously k is going to be up top every time and our iterator is going to be in the bottom. Then we have this term right here, which is going to look like it's going to be k minus our iterator to the power of n. And it looks like we're iterating through all of our flavors, right? J equals 0 to k. You can do a quick sanity check and make sure that this formula matches every single term that you would expect here and up here. Notice there's no 3 choose 3 term that we are subtracting, even though we iterated all the way up through k, but that's just because when we make this here equal to k, this is just going to be 0. So you could essentially say k minus 1 as well, but we're just going to say k because it looks better. So now how does this actually relate to Stirling numbers of the second kind? Well, it turns out this formula is just equal to k factorial times the Stirling number of n comma k. Stirling number of the second kind, that is, because there is a first kind coming later, and you can also denote the second kind ones, I think, as like this, basically. So what do these Stirling numbers of the second kind actually do? Well, you can kind of tell if you just divide both sides of this equation by k factorial. And on this side of the equation, what were we basically doing? Well, we had a set of n elements, and we are partitioning it into k different subsets such that each subset is not empty. And each subset was also distinct, right? Because we had k different flavors, and they're all unique. So when we divide by k factorial, we're kind of getting rid of the uniqueness of each of these k flavors. So what we did is we partitioned an n element set into k non-empty labeled subsets, and with Stirling numbers of the second kind, we partitioned them into non-empty unlabeled subsets. And the difference between them is this k factorial here. So a lot of random jargon, but when you break it down into a concrete problem, like we did here with the ice cream, and we just thought about it using inclusion exclusion, it's actually not that bad. And we'll look into more of these Stirling numbers of the second kind in the future videos.